Hello. In this video, I will be solving problem 3.39 from David J. Griffith's Introduction to Electrodynamics, 4th edition. Now, problem 3.39 wants us to consider two infinite parallel grounded conducting planes of which are both held a distance a apart. A point charge q is placed in the region between them, a distance x from one plate. And problem 3.39 wants us to find the force on q. The second part of the question is checking our answer and seeing that it is correct for the special cases a approaches infinity and the distance x is equal to a over 2. To begin, I'll just draw a simple diagram or figure of our two planes. So we have our first and our second planes. These won't be exactly to scale, but then again, no variables are given. So they are placed a distance a apart. And I'm just going to draw a quick axis, which has no x, y, or z hat value. It's just an axis for distances. And in the middle of our two plates, I will place a charge q. It is not in the center, it is just there for reference. Now, our positive charge q is a distance x from one of our plates. I'm just going to consider the right plate. And in response to our positive charge q, thanks to the principle of superposition, on the outside of our plate, we will have a negative charge q, which is also an x value away from the plate. Now, before we begin solving force, we need to think about two things. First, the fact that positive image charge forces cancel in pairs. When a point charge q is placed between two parallel grounded conducting planes, like in our problem, it induces charges on the planes. These induced charges create an electric field that acts on the original charge q. Now, due to the symmetry of the setup, each positive image charge induced in one plane has an equal and opposite positive image charge induced in the other plane. Therefore, the forces exerted by these positive image charges on the original charge q cancel out pairwise, resulting in no net force from the positive image charge forces. There is, however, a net force from negative image charges. Negative charges are also induced on the plane due to the presence of the positive charge q. These negative charges create an electric field that exerts a force on the original charge q. The net force can be found by considering the contribution of each negative image charge to the force, and that is what we will be doing. Now, to solve for the force, we will use the principle of superposition in electrostatics, and this will allow us to find the net force on a charge by considering the individual contributions from all the other charges in the system. In short, we will use Coulomb's law and the principle of superposition, which states that the total force on a charge is the sum of the forces exerted by all of the forces. Now, I'm going to just continue drawing out these positive and negative charges as seen here in the figure. A distance a away, the same as our two plates, will be another positive and negative charge arrangement, which is 2x apart, which is the same as this, 2x. And again, a away, and these are not to reference, like these are not to scale. Another positive and negative 2x distance away from each other. And this continues infinitely away from the plane. So we again have an a, so on and so forth. And this is repeated on the left side, where a away, we will have another set of negative and positive, which are both 2x away from each other. And this repeats infinitely away from the plane as well on this side. So, to begin solving for force, we will just begin with the simple Coulomb's law equation, which is force is equal to 1 over 4 pi epsilon naught multiplied by q1 and q2 divided by the distance between them. And this is the force acting on q1 from q2. Most often than not throughout this formula solution or problem solution, I will just represent q1 and q2 as q squared, And d will vary thanks to the increasing distance of charges. However, in short, is a sort of relation between a and x. Now, to start calculating our force, we will begin with force is equal to 1 over 4 pi epsilon naught multiplied by negative q and positive q divided by the distance 2x squared. This is just our very simple arrangement right here. This is the force from just these two charges. Well, actually, this is just the force from negative q onto positive q. Now, next, we also need to think about negative q and negative q, which are a distance 2 times a minus x squared. Then we must consider negative q times positive q, a distance 2a plus 2x squared away. In addition, we will consider negative q times negative q over a distance of 2a plus 2 times a minus x squared plus the force from the negative q multiplied by positive q, a distance of 4a plus 2x squared. And additionally, we will consider negative q times negative q, a distance 4a plus 2a minus x squared. And this continues infinitely as, the charges get further and further from the planes. And as you may notice, there's a slight pattern. And before I continue and before I just blatantly describe the pattern, we can reduce our formulas by just multiplying basically just doing this for each one. So we will have force is equal to 1 over 4 pi epsilon naught. And for each of these distances and forces, we will just consider q as squared. So I will pull out q squared from each of them. And from the first, I will just have negative 1 over 2x squared, as you can see here. And it is negative from q times q. Next, I will have positive 1 over 2 times a minus x squared. Next, I will have not positive, 1 over 2a plus x squared. And following that, I will have a positive 1 over 2 times a plus a minus x squared. And after that, I will have a negative 1 over 2 times 2a plus x squared as the distance. Then I will have a positive 1 over 2 times 2a plus a minus x squared. And this continues on and on. If we reduce this one more time by multiplying our 2's and into our parentheses, we will then get that force is equal to 1 over 4 pi epsilon naught q squared times negative 1 over 4x squared plus 1 over 4 times a minus x squared minus 1 over 4 times a plus x squared plus 1 over 4 times 2a minus x squared minus 1 over 4 times 2a plus x squared plus 1 over 4 times 3a minus x squared. And this continues on and on. And at this point, you may be observing sort of a pattern. But before I point it out, I'm going to pull the 4 out from each denominator. So I will have force is equal to 1 over 4 pi epsilon naught q squared over 4 multiplied by negative 1 over x squared plus 1 over a minus x squared minus 1 over a plus x squared plus 1 over 2a minus x squared minus 1 over 2a plus x squared plus 1 over 3a minus x squared. And this will continue on and on. And now, as you can very easily determine, that there is a pattern here. The next value in our just the force equation would be a negative 1 over 3a plus x squared, which is just the negative value of that, and the negative x turns into positive x. And this continues on for 1 over 4a minus x squared, and then it swaps to negative, as this is the counter side from symmetry, 4a plus x squared, so on and so forth. And this is really the beauty of the principle of superposition in this problem. Now we could leave this force as it is, or we could separate it. Which, by separate, I mean just moving the positive and negative values into their own parentheses, which you will see here as force is equal to 1 over 4 pi epsilon naught multiplied by q squared over 4. And now I'll have all the positive values, 1 over a minus x squared plus 1 over 2a minus x squared plus 1 over 3a minus x squared, so on. And then I will have all of the negative, which is negative 1 over x squared, negative 1 over a plus x squared, and negative 1 over 2a plus x squared, negative 1 over 3a plus x squared, and so on and so forth. And this, as we can see here, is the formula and result for the force acting on the point charge Q placed within our two infinite parallel grounded conducting planes, a distance a apart, where Q is x distance from one plane. Now, the second part of our question asks to check our answers for a approaches infinity, and also when x is equal to a over 2. Now, when the separation between the two conducting planes, a approaches infinity, the contribution from the negative image charges will become negligible compared to the contribution from the original charge and its image charge. This is because as a becomes very large, the image charges become much farther away from the original charge compared to the distance x from the original charge to one of the planes. In this limit, only the term involving the distance x survives in the expression for the net force. This term corresponds to the force between the original charge and its image charge on the closest conducting plane. Therefore, the net force simplifies to F is equal to negative 1 over 4 pi epsilon naught multiplied by q squared over 2x squared. And I will show this here. When A approaches infinity, all of these values, one second, approach 0, except for the 1 over x squared. Thanks to that, force is simply 1 over 4 pi epsilon naught, negative, of course, from the negative 1 over x squared, multiplied by q squared over 2x squared. And this checks out. It's also the same as for only one plane. Now, when x is equal to a over 2, we can simply check this by plugging this into our equation, which will give us force is equal to 1 over 4 pi epsilon naught q squared over 4 times 1 over a over 2 squared plus 1 over 3a squared plus 1 over 5a squared, and so on and so forth, and their corresponding negative values, which is just negative 1 over a over 2 squared, negative 1 over 3a 2 squared, and negative 1 over 5a halves squared, and so on and so forth. And as you can see here, these just cancel out with each other. And if you're wondering how we got a over 2 like here, or how we got 3a over 2, it's simply when you plug in x is equal to a over 2, for 1 over a minus x squared, you get 1 over a minus a over 2 squared, which just reduces to 1 over a halves squared. And for 1 over 3a over 2, you plug in x is equal to a over 2. So we get 1 over 2a minus a over 2 squared, which reduces to 1 over 3a halves squared. And that's how we got each of those. And since they each cancel out with each other, we will get force is equal to 1 over 4 pi epsilon naught q squared over 4 times 0, which just gives us a force of 0. Now, when x is equal to a over 2, the distances from the original charge to the conducting planes are equal, and so are the distances from the image charges to the planes. Therefore, the forces exerted by the original charge and its image charge on each conducting plane cancel each other out perfectly. And this is why we should expect a force of 0, and why when we checked and got 0, it proves our answer is correct for this special case. Thank you.